Hey guys, today we are taking a look at our 8.4 notes for pre-calc, which is all about trig identities and kind of relationships between different trig functions. So we have a whole big list of trig identities that are listed on our trig identities reference sheet, which will be provided for you that you're able to use on the test. Some of these we're already familiar with. Our reciprocal identities and our quotient identities is just how they're related to each other in terms of reciprocals. So again, our big three trig functions with sine, cosine, tangent, and then those three reciprocal functions with our secant, cosecant, cotangent. Which ones are paired up with each other, and they're called the reciprocal functions because they are reciprocals of each other. We've also talked about the quotient identities, which would be tangent and cotangent, being sine and sine over cosine, and then cosine over sine. We use that when we're talking about our unit circle. So again, all of these are ones we're familiar with already. We also have a couple of new identities just being things that equations we know that are true amongst our different trig functions. So we've got three different what we call Pythagorean identities, because they're that Pythagoras group back in ancient Greece discovered them, established these relationships as being true. Those really smart old dead dudes that figured out some cool math because they were super bored. We've got three different trig equations, trig identities that are considered Pythagorean identities, and these are all just different rearrangements of those three identities. So my far left column here is my sine and cosine identity, which is sine squared plus cosine squared is 1. Our middle row, most commonly shown as tangent squared plus 1 equals secant squared. And then our last one, 1 plus cotangent squared equals my cosecant squared. And then the two rows underneath them are just different rearranged versions of what those three original trig identities are. It's just going to be how they might present. So again, that top row is the most common way that it's listed. In my middle row, we can see if we solved for sine squared, if we solved for tangent squared or cotangent squared, that's what it would look like. And then my bottom row, if we solve for cosecant squared, or very commonly those bottom rows in my middle and my far right column. Sometimes when I might have to manipulate stuff and utilize those secant squared minus cotangent squared as being just 1. So if we have to add in some extra terms to make stuff simplify out, we can kind of do that with positive 1s with those bottom two rows in columns 2 and 3. Our last ones, very, very uncommonly used, or sorry, not very, very uncommonly, less commonly used, are our negative and our cofunction identities. Negative identity is just kind of being what happens when I plug in a negative x value into my function. Sometimes it spits the same thing back out. Sometimes it flips my sign. Sometimes, it both could happen. And then our cofunction identities, this is what happens as we kind of add and subtract from 90. So all four of these, 6 of them, here we go, 6 of them, 6 trig functions, are equivalent with the other ones that they're equivalent to where we subtract our angle from 90. So if you have something where it's 90 minus my x value or theta, depending on how your equation is set up, that would be our trig identities. So all of these, they are something that in the long run, by the time those who are moving on to calc next year, who are going to be taking the AP class or the AP test, this is something that is expected to be memorized. But for right now, I'm totally comfortable with us just being able to use them properly, and we'll work on the memorization part when we get to that. All right, so I'm not going to keep kind of bouncing back and forth between my trig identity sheet and the notes that we're about to take a look at. So just make sure you have this out and handy so that we can continue referencing it. I will talk about what I'm using, like which trig identity I'm utilizing to simplify or kind of how I'm replacing things. But I'm just not going to keep flipping back and forth to save us some time. So when we are working with these problems, there are two different kinds of problems that we're going to be presented with. One is just going to be simplify the expression. So we're just trying to get it from a bunch of different terms down into as few number of terms as possible. So we're just going to be starting with something. We're going to be replacing things, utilizing our trig identities to try and simplify it down, get stuff to cancel out, get stuff to reduce, that kind of stuff, to get it simplified down into a single term. The other style that we can have is a trig equation that we are trying to prove being true. So we have two sides to an equation, and we're trying to show that equation is accurate. We're trying to prove that it's true using those trig identities. So in these problems, if we're asked to simplify, there's not going to be two sides to work with. We're just working on simplifying it. So my suggestion, if you're stuck, if there's nothing obvious to you as things that you can replace or simplify, you don't identify any trig identities right away as something that we can do, when in doubt, just write off everything in terms of sine and cosine. Because as we saw on the identities sheet, our reciprocal functions and tangent and cotangent, all four of those other trig functions can be written in terms of sine and cosine. So sine and cosine being kind of our most base kind of building block of trig, just like in our unit circle, they were our x and our y values for the terminal points. We can put everything in terms of sines and cosines, and that's usually going to be a good thing to start with. If there's nothing obvious as what could cancel out or what you could replace, put everything in terms of sine and cosine, reduce stuff, factor stuff out, and kind of go from there. All right, so let's go ahead and just hop into our first one here. In number 1, we were asked to simplify secant x minus sine x tangent x. So again, there's nothing obvious sticking out here. I don't have any, sine squareds, cosine squareds, that kind of stuff. I'm going to just go ahead and just put everything in terms of sine and cosine. Sorry, my light turned off because I'm sitting too still. So I'm going to go ahead and just put all of these in terms of sine and cosine. So secant, that is my reciprocal function for cosine. So secant is 1 over cosine. Sine is already in terms of sine and cosine. And then tangent, that is sine over cosine. I'm probably going to just start skipping writing my variable in the middle of the problem. I'll make sure I put it back in at the end. But as you can see, I kind of gave up on writing tangent x, sine x, that kind of stuff pretty early in the problem. So from here, I can kind of combine my two terms together. I've got 1 over cosine minus, this would be sine squared over cosine. Because again, if I do sine times sine, that's sine squared. So we see here I can collect my like terms. I do have a common denominator. That would give me 1 minus sine squared over cosine. So from here, as soon as I see stuff where it's squared, especially when you have multiple different terms, this is where you're going to want to go to those Pythagorean identities to try and see if this is one of those expressions. So we should see in my Pythagorean identity the bottom row, 1 minus sine squared is equivalent to cosine squared. So if we've got cosine squared over cosine, I can reduce a cosine from top and bottom, and my simplified answer here is just cosine of x. So that would be the simplified answer for number 1. That's it. And we know we're done. Obviously, it's down to as simple of a term as can be. Our goal for these is always to get it down into a single trig function. So if we can get it down to just a cosine, a sine, a secant, a cosecant, a tangent, a cotangent, then as long as it's down to that single term, we're good to go. So hopping into number 2 here, we are asked to show in this case that cotangent of A times 1 plus tangent squared of A all over tangent of A is equal to cosecant squared. So when we're working with these equations, it is usually, not always the case, usually easiest to pick the messy side and try and simplify it down into being equivalent to what's on that right side. So what we're going to do here for number 2 is we're going to show that messy left side, cotangent times 1 plus tangent squared all over tangent, is equivalent to cosecant squared. So in here, I recognize my parenthesis 1 plus tangent squared. That's one of my Pythagorean identities. So I'm going to go ahead and start by replacing my parenthesis with just a secant squared. So we've got, jumped the gun here. We've got cotangent times secant squared all over tangent. So I don't see anything else obvious to do moving forward here other than, putting secant squared back in as 1 plus tangent squared. There's no other reciprocal functions or anything I can do here. So I'm going to go ahead and just put this back, everything in terms of sines and cosines. So cotangent, that is cosine over sine. Secant is 1 over cosine, so secant squared would be 1 over cosine squared. And then tangent, of course, is sine over cosine. So I can go ahead up top here, cancel out a cosine with the cosine in the bottom. So that gives me 1 over sine times cosine over sine over cosine. So do a little bit of fraction work here. If I'm dividing by sine over cosine, I can multiply by the reciprocal. So I'm going to move this all the way over here because I'm going to run a horizontal room. So 1 over sine cosine times cosine over sine, right? Because I'm multiplying by the reciprocal. That reciprocal tangent was sine over cosine, so I'm going to multiply by cosine over sine. I'm going to cancel out my cosines that are common top and bottom. That gives me 1 over sine squared, which, again, this is technically down into a single trig function, but we can do a little bit better. We can get that not as a fraction anymore. We know that the reciprocal of sine is cosecant, so I can write this as, CSC, cosecant squared of A. Which, oh hey, that's actually not just how we want it, like how is the most simplified. We are trying to show that it was equivalent to that right side with cosecant squared. So not only is that actually more simplified, it is equal to that right side that we were trying to show that is equivalent to. All right, a couple of more here, a couple more examples. For number 3, we asked to simplify sine of theta, secant of theta, cotangent of theta. So again, nothing obvious here. I don't have any squares. I'm going to go ahead and just put everything in terms of sines and cosines. So that would be sine times 1 over cosine, because that's reciprocal of secant. And then cotangent, that is cosine over sine. Which we should get excited here because look at this. We got cosines canceling out top and bottom, sines canceling out top and bottom. It feels super weird, but our answer here is just 1. We multiply those 3 trig functions together, everything cancels out, it's just 1. Great, awesome. Okay, flying along here. Number 4, we're asked to simplify 1 plus tangent squared of x minus 90. Okay, now this one a little bit tricky because not only it's super tempting to look at my 1 plus tangent squared and just do my Pythagorean identity right away, but I can't do that unless this is just x. So because I have x minus 90 in here, I can't do my Pythagorean identity yet. I'm going to have to do a little bit of reworking of stuff and then, do maybe a Pythagorean identity at the end. Okay. So the other thing, like what we should notice here, obviously we've got x minus 90 inside my trig function, but not only does that tell us that we want to be dealing with one of these co-function identities, tangent of 90 minus x squared, we see that right here. That being equivalent to cotangent, but my subtraction is in the wrong order, right? The way that my problem is showing me my tangent is x minus 90, not 90 minus x. And I have to have it as 90 minus x in order to be able to use that co-function identity. So not only do I have to do a little bit of scratch work beforehand to be able to do my Pythagorean identity with 1 plus tangent squared, I also have to do a little bit of scratch work before I can even do my co-function stuff. So what I'm going to have to do here, this is equivalent to 90 minus x if I factor out a negative from inside here. Right, I can do that. I'm allowed to switch the order of my subtraction if I factor out a negative. So that would be 1 plus negative tangent squared of 90 minus x. Sorry, squared is out here now. Because, again, this is like tangent of x minus 90 times tangent of x minus 90. So I factor out those negatives, and it's there, but it is still squared. So I'm going to go ahead and now do my cofunction substitution. My cofunction for tan of 90 minus x was cotangent of x. So 1 plus negative cotangent of x squared. When I square a negative, it's going to become a positive, so I get to drop that negative sign. So this is 1 plus cotangent squared of x. And now it is one of our Pythagorean identities. It's not the one that I originally thought I was going to be using because I started with 1 plus tangent squared, which is that middle trig identity, my middle Pythagorean identity. But I'm actually using 1 plus cotangent squared, which is my far right trig identity. So I'm going to go ahead and do this substitution. This is just secant squared of x. Okay, there we go. Secant squared of x. Oh, sorry. With my original thought, it is actually cosecant squared. Right, because 1 plus cotangent squared is equal to cosecant squared for that Pythagorean identity. Almost made a mistake. No bueno. All right. Number 5. We've got 3 more. Oof. Moving along here. So number 5, we are asked to simplify cosecant of x times cosine cubed x tangent x minus sine of x. So I see nothing obvious right away. I'm going to put everything in terms of sines and cosines. It's usually a good place to start. So cosecant being 1 over sine. Cosine is obviously already in terms of sines and cosines. Tangent is sine over cosine. And then sine, once again, already as sine. So I can reduce this cosine here. So this is now 1 minus sine cosine squared sine minus sine after I reduce. So what I can do now, inside my parenthesis, I recognize that I've got 2 terms that both have sine in them. So I'm going to factor that sine out. So that's going to give me 1 over sine times cosine squared minus 1 is what I end up with after I factor it out. So now a couple of things are going to happen, and I'm going to do this just simultaneously because here my sines cancel. And then what else do we got here? So we've got 1 out in front there. So cosine squared minus 1. We're going to be using, again, one of those trig identities from my Pythagorean ones. But we should notice here the order that we use it in my Pythagorean identity for kind of left middle is 1 minus cosine squared. But we have it as cosine squared minus 1. So we're going to have to do that same thing we did on the previous question and factor out a negative 1. So this is going to be negative 1 minus cosine squared to be able to flip the order of that subtraction so that I can substitute sine squared in here. So this is negative sine squared of, what was our variable? X. Okay. All right, last 2, and they're both equation solving ones, or proving equations, and they're both kind of nastier ones. So with these, I could start by putting everything in terms of sines and cosines, but it's not going to be super useful to me right away to be able to do that because I'm trying to show, again, based on how I would suggest doing the problem, I'm going to take the nasty side, try and make it look like the nice side. So I'm trying to show that 1 over 1 minus secant plus 1 over 1 plus secant is equivalent to negative 2 cotangent squared. So before I put everything in terms of sines and cosines, I might as well try and combine things together, especially since these are both already the same trig function. They're both secant. It's going to be in my best interest to try and simplify it as best I can with just algebraic things. And then from there, see if I need to put stuff in terms of sines and cosines. Okay. So I'm going to try and add these 2 together. If we're trying to add 2 fractions, remember we need a common denominator. So I'm going to multiply by what's missing. All right, so if I multiply by what's missing, this becomes a 1 plus secant times, So it was originally 1 minus secant down below for this first fraction. And I had to multiply by 1 plus secant on top and bottom. And then my second fraction here, I had to multiply by 1 minus secant to get it to be a common denominator. It was originally 1 plus secant. So 1 minus secant. Because my common denominator is the 2 denominators, basically. 1 minus secant, 1 plus secant. Those are my 2 factors. I multiply those 2 fractions together, those 2 parentheses together to get my least common denominator. But I had to multiply by what was missing. So when I combine my like terms now, up top I have, switch my colors up, 1 plus secant plus 1 minus secant all over 1 plus secant, 1 minus secant, secant. So up top, my secants are going to cancel out, or they're going to add up to 0, basically. They're going to cancel each other out. So I end up with a 2 up top. So I'm going to move this down here, the next layer. So I have a 2 up top. Now down below, we don't usually FOIL them out to kind of simplify it together when we're working with adding two rational equations together, rational functions together. But in this case, what I should recognize, or what I recognize here in this case, 1 plus secant, 1 minus secant, it is a difference 2 squares shortcut. Right? I've got the same two terms, once they're positive, once they're negative. So if I FOIL these together, or I'm going to just use my difference 2 squares shortcut, this ends up being 1 squared minus secant squared, which 1 squared is 1, secant squared is secant squared. So I've got that. And now, again, I look to my Pythagorean identities to see if there's a secant squared thing that I can substitute, which I recognize on my cheat sheet that secant squared minus 1 is tangent squared. So if I can flip my order here, because again, right now it's 1 minus secant squared, I'm going to factor out a negative 1, and then I can flip this to secant squared minus 1. That's something I'm allowed to do. If I factor out a negative, it's going to just change the order that I'm subtracting in. So now I'm going to do something else. I've got 2 over negative. I can do that substitution with my Pythagorean identity of secant squared minus 1 being tangent squared. And if I'm trying now, because right now I've got it down kind of simplified as far as I immediately recognize. But let's take a step back and remember what's our goal. We're trying to show that this is equivalent to negative 2 cotangent squared. So if cotangent is just the reciprocal of tangent, then all I have to do is flip this over because my tangent squared is my denominator. So my negative comes along for the ride, 2, whoops, not cosine, cotangent squared of x. And that is enough to prove that that is the case. All right, last one, chat. We're asked to prove in this case that cotangent of theta, 1 plus tangent squared of theta, all over tangent of theta is equal to cosecant squared. Now, this one I didn't recognize until this very moment. This is the exact same problem as number 2. So we're going to just call that a day, because even though I'm using thetas instead of capital A's, it is still the exact same trig functions, trig substitutions. So again, like in this case, I would do a substitution of 1 plus tangent squared with secant squared. So cotangent times secant all over tangent, which I then would do my sine cosine flips. So this would be cosine over sine times 1 over cosine all over sine over cosine. They cancel out here. That was, oops, cosecant, so secant squared. So this was cosine squared. So we've got 1 over sine cosine over sine over cosine. So we flip to multiply 1 over cosine sine times sine over cosine. My sines cancel. 1 over cosine squared is equivalent to cosecant squared of theta. So I said we were going to skip it and just plowed through it real quick. So that is it for our notes for 8.4 for relationships amongst our trig functions. We are going to have a practice day on this. This is something that we will utilize and kind of fold it back in with 8.1 when we're solving our trig equations. Obviously, we're going to be kind of using these to manipulate our equations to be able to get something simplified down to the point where we can solve it using our calculator. So that is all I got for you guys for today. So as always, if you guys have any questions, concerns, thoughts, ideas, hopes, or dreams, make sure you guys are reaching out and letting me know. Otherwise, have a great day. We'll see you soon.